So now moving on. So the first 6 lessons, I was just trying to talk about what an integral is, the problem I'm trying to answer, and then some techniques that we're going to use in 461 and in later courses for evaluating integrals. Now I need some special results. In particular, what I'm driving at is this differentiating improper integrals, because this is going to be something you need to be able to do when you want to work with the Black-Scholes pricing formula. And so I'm going to first get started by just differentiating definite integrals. Then I'll introduce what an improper integral is, and then we will learn how to take their derivatives. So this is actually not too difficult of a topic, so hopefully this set will go by quickly. So I'll first start out by pointing out that a definite integral, so if I integrate a function f of x over an interval a, b, that's a real number. So it's constant, it's not changing. So if I try and take the derivative of this function, it's constant, so its derivative is 0. So the only way this is going to get exciting is if the limits, so the a and the b, are now functions of another variable, so I chose t, then when I evaluate this definite integral, it's still going to be a function of t, and so I might want to consider taking its derivative with respect to t. And then more generally, the integrand can also have t in it, but since we haven't talked about functions of more than one variable yet, I'm going to leave that for lesson 3. And so the question we want to consider is, how can I calculate the derivative with respect to t of the integral of a function f of x where the limits are functions of the value t? So it's actually pretty straightforward. If I wanted to just evaluate this integral, what I would do is find an antiderivative of my function, and then by the fundamental theorem of calculus, I could evaluate this integral. It's just going to be the antiderivative evaluated at the top endpoint and the antiderivative evaluated at the bottom endpoint. And now if I take the derivative of this, well, all I have here is a function of a function. So I can take the derivative of that using the chain rule. And so what I'm going to get is g prime of t. So g is a function of t, so I'm taking its derivative with respect to t. That's just going to be equal to the derivative of the outside function evaluated at the inside function. And then by the chain rule, I have to also multiply that by the derivative of the inside function. And it looks a little bit complicated, but all I'm doing is just I have to do it once for the upper endpoint and once for the lower endpoint. And then by the way we've defined this capital F, I know its derivative is lowercase f. So the formula for differentiating a definite integral is just going to be f of b of t times b prime of t minus f of a of t times a prime of t. And so just to state it with all of its actual conditions, so this is the definition that came out of the course textbook. So f has to be a continuous function, and a of t and b of t have to be differentiable functions. Then the derivative with respect to t of the integral from a of t to b of t of f of x dx is just f of b of t times b prime of t minus f of a of t times a prime of t. And so just a quick example of this. I think this is my simplified version of exercise 11 from chapter 1. So let's let g of x be defined as 1 over the square root of 2 pi times the integral from 0 to b of x of e to the minus t squared over 2. And then b of x is just going to be defined by this function here, which can be simplified the way I've done it in the light gray on the right. And so this is actually a calculation you'll come across These are sort of pieces of the Black-Scholes pricing formula. So this is the interest rate. This is the volatility. But again, since I haven't talked about functions of multiple variables yet, I just wanted to plug in specific numbers so it doesn't get too confusing about what I'm actually trying to do. And so the goal then is to compute g prime of x. And so this is the formula from the previous slide. But now since my lower limit is 0, so it's constant with respect to x, if I take its derivative, this a prime of t is just going to be equal to 0, so the derivative of a constant. So this formula will simplify a bit because of a being equal to 0. So all I need to do is just evaluate my function and then multiply by the derivative of the inside. So the first step I will do is just evaluate my function g of x. So this bit here, I'm just going to evaluate that at b. And so I had 5 times log of x plus 0.06. So when I square that, I'm going to end up with 25 times the log of x plus 0.06, that quantity squared. And then I still need to multiply it by the derivative then of b of x. So b of x was equal to 5 times the log of x plus 0.06. And so that's pretty easy to see the derivative of. That's 5 times log of x. That's derivative is 5 divided by x. And 5 times 0.06, that's just going to be a constant, so we don't even need to bother doing the math. That's going to have a derivative of 0. So b prime of x is just going to be 5 divided by x. And so now I just need to put all of the pieces together, which just means substituting in 5 over x for b prime of x. And that gives me the derivative of my function g of x.